Hello, my name is Andrew Penner, and I'm the president of the AEE Canada East chapter. Before we get rolling on today's webinar, I just wanted to give a quick shout out to our sponsors. Sponsors are so important to chapters like ours. They enable us to fulfill our mission financially. And through their support, they confirm our relevance and provide credibility. They expose our members to new ideas and ways of thinking, and they help us grow our network and influence. So this is what you see on the screen is the stable of sponsors that our chapter enjoys for 2024. If you're watching, you don't see your company represented there, and you think it should be, then we would welcome you to reach out to us at the chapter, and we'd love to have a conversation about how we can help each other and continue to share the mission of energy efficiency and decarbonization. As a chapter of the Association of Energy Engineers, the AEE Canada East looks to espouse the mission and values of AEE. We are the local expression of AEE, and for some, we represent their sole window into the International Association. So as an association, it was founded in 1977, so it's been around for a good long time. It has grown to include more than 18,000 members across more than 100 countries. And there are over 90 chapters just like ours doing this kind of work. If you're not familiar with our chapter, you'd like to learn more, you can head on over to our website. It's there on the screen. And we'd be happy to engage with you more. So without further ado, we're going to start today's topic. So we're focusing today on panelized deep retrofits. This is a really interesting topic, and I'm really excited to learn more about it. Lori is our presenter today, and she's a co-founder of Habit Studio. It's an award-winning architectural and residential design practice, and specializes in sustainable renovations and custom passive houses. She's a co-founder and design director of the Recover Initiative, which is a nonprofit deep retrofit accelerator focused on developing and scaling deep retrofit solutions. So she is an authority in this topic. As a building science specialist, she's passionate about integrating passive house performance and biophilic design principles into her work. And as an instructor with Passive House Canada and a board member of Retrofit Canada and Passive Buildings Canada, she is a champion and advocate for high performance buildings across the country. So Lori, with that, I'm going to stop being a talking head and allow you to take the reins. And again, I'm really looking forward to hearing all about panelized deep retrofits.
Thanks, Andrew. Just 2 seconds while I switch to my slides here. So thank you so much for joining me in today. I am very much an advocate for retrofits, so I'm always excited to have an opportunity to talk to some new folks about this topic. And so, yeah, Recover, just like a couple of minutes about who Recover is and what we do. We established Recover in just very early 2020, leading into the pandemic. We see a small group of us received a small pot of money from the Nova Scotia government to do sort of a case study, which I'll share with you in a minute, looking at prefabricated panelized retrofit potential for Nova Scotia. And that's because, the greenest building is the one that already exists. I'm sure you've all heard that before. And so Recover really was established to develop some retrofit solutions that respond to the climate crisis at speed and at scale. And just it became very timely. Like we sort of grew really quickly because we did this first study. And then in July of 2020, we did a webinar, and so many people were stuck in their houses that over 100 people attended our webinar, and we're this sort of small, scrappy group from Nova Scotia who we didn't think anybody even knew who we were. And so to get 100 people at our webinar was pretty cool. So this is our core team. Emma Norton is our operations director. Me, I'm responsible for design. And Nick Rudnicki, who has been our technical director, he's actually stepping away from Recover, but he has been instrumental up to this point in all of our projects. And Amanda McNeil is a project manager. So that's our core team. And
hey, Lori, I'm seeing the Recover desktop, but I'm not seeing the
oh,
slides.
It's not coming. Okay, well, that's great. Let me try again. see it now?
That's better. That's
Okay.
better. Thank you.
So, okay. Thank you. Okay. So there's our core team. And so for pretty much all of our projects, we have sort of carried through the same core objectives. So looking at developing solutions that are net zero carbon and net zero energy or net zero energy ready, and knowing that net zero carbon is like kind of like the pinnacle, not really achievable yet, but that should be our ultimate goal. Minimal embodied carbon, so we don't want to be implementing retrofit solutions that save operational energy at the expense of, kind of emitting an extreme amount of carbon in the process of construction. Minimal occupant disruption. We have to retrofit most of the buildings in this country. We've already got a housing crisis. We can't displace people to do all the retrofits that we need to do. And so what ways can we, are there ways we can address this? And then the lowest total cost of building ownership, or TCBO for short. So I'll talk about that a little bit further on. And, we're trying to evaluate projects in a different way. We frequently, for decades in our industry, have evaluated measures based on simple payback or return on investment, but that's not really an appropriate measure for projects where you're implementing like multiple upgrades at once. It's a really great metric for evaluating, adding solar panels or standalone changes. But when you have something that's as complex as a building where all of the systems performance are interrelated, it's not right. The evaluation is kind of skewed. And so we look at TCBO, which looks at kind of it looks at a 60-year life cycle costing with everything that we can imagine might need to happen to the building, including the sort of maintenance and servicing cycles. So however many times you need to replace a roof in that time frame, however many times a heating system needs attention. So initially, all of our first studies looked at can we adapt the Energy Sprong model to the Canadian context? And so Energy Sprong essentially is this graphic talks only about the kind of envelope and measures that happen, but there's a LiDAR scan of the building or other kind of scanning of the building, factory assembled or offsite prefabricated panels brought to site and bolted onto the building. We've historically, all of our interest in Recover was really envelope focused before mechanicals. Like we always need to, once you kind of tighten up the building and improve the thermal performance to the extent that we're talking about, then additional work is needed to make sure that like a lot of these buildings don't even have ventilation, mechanical ventilation. So we need to make sure that we introduce fresh air, and likely the heating system is going to, hopefully the heating system is electrified and made considerably more energy efficient. So that's kind of the whole process. Energy Sprong originated in the Netherlands. They have an entire market development business model complete with finance mechanism. So our team has not been looking at the financial angle. We're really looking just at like what we do to the building, the technical side of it so far. And the reason we looked at Energy Sprong is because it is the only retrofit initiative globally to have successfully scaled itself that to our knowledge that we've encountered. So over the first 5 years of Energy Sprong being implemented, they reduced the cost of implementation by 50%, and they sped it up by more than 50%. So they were able to achieve a lot of economies of scale. And our buildings are not as simple in terms of kind of form factor and building typology as the Netherlands, and so we don't think that it's going to be appropriate for all buildings in Canada, but we're trying to figure out which ones it makes sense for. So this was our first project. So as I said, this was supported by the Nova Scotia Department of Natural Resources and Renewables. And so we did a study looking at how a panelized prefabricated retrofit, sort of the potential energy savings and cost to implement on this 1980s apartment building in Halifax. It's a pretty small apartment building. It's just 4 stories and 4 units. Aside from the kind of fancy 1980s mansard roof, it was a quite simple building in terms of the form. And we had willing owners. I mean, that was really largely what, we had an owner who was willing to let us get up close and personal with their building. So that project, we studied it for about 6 weeks, and we had a proposed panel design. It's very similar to what I'm going to show you later in the slide deck. And essentially we swapped out the oil-fired heating equipment for heat pumps and wrapped the building in panels and filled the roof with PV. And that looked like a transition from about 90,000 kilowatt hours of energy annually down to 24,000. So dramatically reduced the energy use of the building, and at 24,000 kilowatt hours of energy, we were able to offset that entirely with rooftop solar. And then the thing that we care a lot about, but is like imperfect. There's no consensus on how we measure this or what we do about it. But we did calculate the embodied carbon associated with a panelized retrofit approach. And our panels, which you'll see, they're filled with cellulose insulation. And so we were actually storing carbon in the building. And so the panels have about 28 metric tons of carbon. Oh, sorry, I take that back. The slide isn't even about that. So we we've prevented 28 metric tons of carbon emissions in this, and we've stored 50 metric tons of carbon in the building. Our TCBO model showed that over 60 years, doing this project would save about $1.5 million in operational expense. And that at the time that we priced this project in 2020, the cost to do the retrofit was estimated at $350,000. The anticipated time on site was around a month, and that was contrasted with if we were to do a conventional retrofit to the building, it would take probably 9 months to a year. This project has not taken place. None of our projects have actually gone forward yet. We're in talks now about going forward with some demonstration projects, but these are all just case studies, FYI. So after we did that project, we went from working on a tiny little building in Halifax to getting in front of Toronto Community Housing. That was a little bit of a whirlwind. They have the largest portfolio of affordable housing in the country, over 5,000 buildings, and they have a commitment to decarbonize their entire portfolio by at least 25% by 2028 through the National Co-Investment Fund, so through CMHC. And they've primarily been focused on tower retrofits or large apartment buildings, but a large part of their building stock is in townhouses, and they were interested in finding out if an energy strong approach would work for their townhouse portfolio. So that's about 780 townhouse blocks is in under their ownership, and a lot of them are similar to this building. So this project is at Scarletwood Court. It's a late 1960s or early 1970s masonry townhouse block, and it's got a considerable maintenance backlog, which is pretty par for the course for Toronto community housing's townhouses. And because Energy Strong work really is implemented quite extensively on townhouses, it is felt to be a promising pathway forward for TCH. So we studied this building over the summer of 2021, and again, we did a similar process to what we did with our Halifax project. This one was interesting because in the Halifax project, it was a little bit nebulous whether we could actually panelize the roof. In the end, we decided that it was viable, but it was challenging. But in this case, we developed a design that panels could wrap up and around the whole building quite confidently. And so this cross-section gives you a sense of the level of detail that we took the study to. It's not ready to deploy, but we took it through the schematic design phase of a project and partway through design development, in that we had engineering done and had costing done, but it's not done to full construction drawings yet. On the Halifax project, we looked at simply swapping out the mechanicals in the existing mechanical room in their boiler room and electrifying. But with Toronto Community Housing, we looked at one other aspect of Energy Strong projects. Frequently, or almost always, they have these mechanical pods, which are essentially a box that would get installed on the outside of every building. And that box has a heat pump, it has ventilation, and it has hot water heater included in the box. We analyzed this, and it makes a lot of sense in the European context, because these buildings are typically like slab on grade or fully occupied. TCH didn't go for this with this building ultimately because they've got a basement room that can hold the mechanicals, but it's the company that we sort of was aligned with us on this project is called Build Equinox, and they're actually working on making these mechanical pods deployable in North America. It's a Chicago-based company. So in this case, it's these are all North American components. There's a Rheem hybrid heat pump and a Serve ventilation unit, and I think a 1.5 ton high efficiency heat pump, air to water heat pump. So on this project, it's on all of our projects really. We haven't just kind of looked at base case and taking it to net zero energy ready or net zero performance. We look at sort of a range of performance targets, partly because a lot of people might just take these buildings to code minimum, and partly because there's a lot of sort of cost impacts with every increased level of performance that you go to. And so for this one, we looked at the base case, so that's the business as usual. And then we looked at minimum building enclosure upgrades, bringing the enclosures to code minimum. And then we looked at additional measures, adding the mechanicals to that and adding different kind of performance of level of insulation in the envelope. And really, even the first improvement from business as usual to building code minimum was about a 65% energy use reduction in this project. And then if we took it all the way to net zero energy ready, it's an 88% energy savings. There's a lot of existing mature trees on this site. And so we did not recommend that they put solar panels on the roof. If they were able to do solar offsite and put that towards the building, then they could get down to about 88% energy savings in this project. And for the embodied carbon for this building, we didn't just, in our first building, we just said we know that insulation that's plant-based is going to store carbon in the building, but we didn't do an extensive comparison to prove that. So in this case, in this project, we did. We kind of wanted to look at what are some typical ways that we would probably add insulation, with adding either rigid insulation to the outside of the building, or with spray foam, or possibly with mineral wool. Like, all of those seem like viable ways that somebody might do a conventional retrofit on this project. And we compared those to our cellulose-based Larsen Truss panels. And for all of the kind of conventional scenarios that we examined, our panels, even though they do have a carbon footprint, there are some emissions up front. They're at least half as much as any other option that we looked at. And then looking at the 60-year kind of life cycle cost breakdown, which again includes everything that you can kind of think about right now to predict might be spent on the building. Interestingly, sort of a lot, all of our scenarios represented significant savings to TCH, with the kind of net zero energy ready and net zero performance being the best. And all three of those kind of last scenarios had about a 30% improvement in TCDO over 60 years. So from just under $12 million over 60 years down to 7 and, just under 8, really. One thing to note with this project is that we estimated that the construction cost was going to be about $1.4 million to do a panelized retrofit on the project, but that there would actually need to be another around $500,000 in work needed to these buildings because of just interiors work related to their existing maintenance backlog. Like they have had, TCH, just their portfolio has a lot of maintenance backlog across the board, and their typical practices are to kind of spread the money around. So to do incremental repairs as needed, or they're really putting out fires and addressing the most urgent issues, and they need to get to a place where they're kind of proactively getting all of the buildings up to a better standard. So those were our first two projects, and we learned a lot on them. And then as we were wrapping up the TCH project, we came to an agreement with NRCan to do a study on panelized deep retrofits of municipal buildings. So those first two projects looked at residential. We had pretty good results showing, the promising results showing that while these projects are expensive, decarbonizing these buildings is very achievable through a panelized retrofit approach, and the potential to be storing carbon in panels and reducing the upfront carbon burden of doing retrofits is attractive and appealing. And so NRCan was interested in us doing a little bit more. And one of our, so Emma Norton, one of our founders at the time, worked for an organization called Quest Canada, which many of you are probably familiar with. And Quest works with municipalities. And so we kind of grew a really large municipal following and network over the first couple of years of operating. And so many of these municipalities are working on figuring out how they decarbonize their portfolio of municipally owned buildings. And so 6 of them joined us in this project, looking at, can we do prefabricated panels to kind of municipal commercial building. So this was done with Natural Resources Canada, TAF, again, the Nova Scotia Department of Natural Resources and Renewables, Efficiency One, and Quest. And then these are the municipalities, so Colchester, New Glasgow, and Halifax here in Nova Scotia, and then Burlington and Oakville in Ontario, and the city of Saskatoon. So we worked really closely with all of these municipalities for more than a year to do feasibility studies for 6 buildings. And these are the 6 buildings. So 3 of the buildings are community centers. So in Halifax, we had a sort of former fire station turned into a combo community center and daycare center. And in Oakville and Burlington, we had senior centers in each of those cities. And then we also had a water utility building in Colchester. So that building is kind of 50% office and 50% kind of service area for water vehicles and large equipment. And then in New Glasgow, we have the Municipal Operations Building, which effectively is kind of again, a maintenance facility that is used for snowplow maintenance and large trucks and storage of that equipment. And it's housed in a former Kmart. So we were kind of interested in that because we're looking for buildings that in each municipality, we could save them a lot of energy and greenhouse gas emissions, but we're also looking at studying buildings that may be kind of repeatable. So there are buildings that are all across the country, and so big box buildings certainly are that. And finally, the building we looked at in Saskatoon is also a pre-engineered metal building, similar but not quite to the New Glasgow building. And that building was the access transit, bus storage, and dispatch building. And so just because I've only got an hour here today, and because talking about all 6 of these buildings is way longer than that, I've decided to just focus this talk on the 3 Nova Scotia buildings, but the kind of overall learnings that we found in this project, there were some commonalities across all of them, so I'll talk about that. So what we sort of decided up front to look at, again, we had a number of scenarios that we were looking at for each building. NRCan's requirement for the funding stream that we were working under required at least a 50% energy use intensity reduction. And so that was kind of our minimum upgrade. So not necessarily code minimum, but saving 50% of the energy. In our first 2 projects, we were actually, Recover is perhaps naive, but quite ambitious. And so, we really do believe that we only have time to touch every building once before, between now and 2050. And so our overall goal is to have a net zero country by 2050. We need to push building, like 50% isn't really good enough. That's our view. And so we're really looking at 75% energy savings in most buildings in order to get to net zero energy ready. And so we we targeted net zero energy ready performance as a sort of second scenario for each building. And we looked at, we knew that we wanted to be electrifying and promoting heat pumps in these projects, but we really weren't sure. And definitely there's a geographic impact on this, and also sort of site has a bearing on this, but we weren't sure in each case whether an air source or ground source heat pump system was going to be to offer the lowest TCBO over 60 years and to be the most effective for these buildings. So we looked at that for every project. And then as the final scenario, we looked at adding solar panels to the net zero energy ready scenario and bringing the building to net zero energy performance. So for all of the buildings, we designed wall panels that, again, are based on cellulose insulation and just wood framing. And as part of all of this, we did every building had WUFI hygrothermal modeling done to sort of assess the risk associated with adding prefabricated panels made out of wood and cellulose, so plant-based materials, and if there was any risk. In a few cases, some of the assemblies we swapped out plywood for gypsum-based sheathing, for example. These panels were all designed to dry from the inside to the outside, knowing that we couldn't possibly know for sure that there isn't something in all of the existing buildings that could be inhibiting drying to the inside. We had to have them dry to the outside. And, even I think that for any retrofit, if we're going to scale this approach in any capacity, we need to know that the panel itself is going to be able to dry, because even if we do a lot of kind of destructive testing to understand the makeup of a wall, we might never be able to conclusively say what every material in that existing assembly is. So the way that they're designed is that there's a kind of interior strapping, which makes a little bit of a sort of air space against the existing building. It lets us have a little bit of air, can kind of, it's almost like a buffer zone for if any moisture does come from the inside, it can slowly move through. And it lets us shim the panel against these existing buildings because, of course, none of them are straight or square. And then we have a variable permeability vapor control membrane. So that's the layer you see there as the Intello membrane. And so we have that kind of turned inside out from the way that we would typically have it in a normal wall, so that it dries, lets moisture through and dry to the outside. And then we have a wood frame, and our panel design is sort of that if we have a 2x4 or 2x6 frame, or the R value needed would fit in a 2x4 or 2x6 frame, we use just standard framing. And then if we need any deeper than that, then we would kind of have a 2x8 to 12 frame with staggered 2x4 studs to just reduce the wood a little bit. And that is filled with dense packed cellulose. And both of those materials are hygroscopic. They move moisture through. And then we have a layer of plywood sheathing and vapor open water resistive membrane as well on the outside of that. So all of that is kind of our panel. And then on the outside of that, we would have strapping. And when we first proposed, our first couple of projects, we thought that we were going to, we recommended having everything, including windows and cladding, be brought to site as part of the panel, as part of the prefabricated panel. But in this project, we decided to move away from that. We think the panels should be shipped to site basically with, from strapping to strapping, and that the metal be added later, or the siding be added later. Typically, we recommend metal. And that way you have a lot less kind of challenges with making the cladding, lapping the cladding and securing it properly. The reason we recommend metal is because of durability, particularly for municipalities, but really for anybody who's managing a portfolio of buildings over the rest of our lives, really. Like, again, every building we touch, we should touch once and then do the best we can and move on to the next building. And so we don't want to be promoting solutions that lock people into cycles of maintenance requirements. So metal, we really don't have to do anything to keep it in good condition for its useful life. And even though it is a material with a high embodied carbon, it is recyclable at its end of life. So for all of these 6 buildings, we recommended metal siding. So first up was New Glasgow, and this building is about an 80,000 square foot steel and masonry structure from the 1970s. And up until the pandemic, it was used as like a flea market in the old retail area, with New Glasgow's municipal operations in the kind of back old storage and loading area. And we were really optimistic about figuring out a panelized solution for this building because, again, it's building type that's ubiquitous across the country. Nobody really cares what they look like, and generally they're not that attractive. So if you're, unlike a lot of municipal buildings where people are highly opinionated about what they might look like, nobody really cares what a mall looks like. And this building was just kind of all of the buildings that we looked at for these municipalities had very high energy use intensities. And so interestingly, this building, it's huge. So it has a high kind of energy use, but its energy use intensity wasn't that bad compared to some. It was 136 kilowatt hours per meter square per year, except that they only kept the heat set to 7 Celsius. So when we kind of calibrated that to 20 Celsius to kind of reflect normal operations, that brought that up to about 249. So if they were heating it to a comfortable temperature, it would have been a lot more expensive. As it is, it costs over $200,000 to heat this building every year. And so they really need to do something about it. And that equates to about 550,000 kilograms of CO2e being emitted every year. So we came up with a design that wrapped it with 2x4 wall panels, 2x6 recover like roof panels. All of our buildings that in this study, we added passive house level windows, essentially, so triple glazed insulated frames. And in all of the buildings, we added a 90% efficient ERV. So I think across the board, we were looking at replacing our existing ventilation systems with Tempest ERVs. We couldn't, for this building, we cannot come up with a business case to replace the boiler. So while to meet Glasgow's kind of decarbonization goals and to meet Canada's, we need to get that building off of oil. We think that in terms of the business case, they need to keep it till its kind of end of useful life. This is just a graphic of what that looks like. This is one of the few buildings where we were actually able to do a panelized system on the roof, but we did it by adding a new wood roof truss system above the existing. This building, like many metal buildings, and the sort of challenge with steel structure for sure is that they're kind of only engineered to support their own weight. New Glasgow actually insulated the roof of this building a few years ago and had to take the insulation off because the added snow loads was causing like a lot of structural deflection. And so basically we had to, if they were to proceed with this retrofit, they would need to reinforce the steel and do a lot of extensive kind of metal work to do it. Not really, unfortunately, the cost is not viable for them, but we proved that we sort of demonstrated the technical side of it. What that roof looked like is basically the same panel as the walls, but flipped on its side. But because it is cellulose, we need several layers of insulation outboard to just alleviate any dew point risk. And we replaced the plywood sheathing with gypsum-based sheathing. And when we WUFI modeled our roofs, this is interesting and something that I'd like to dig into deeper at some point. We found that we could only make the WUFI modeling work if, so basically that there would be no risk of condensation happening inside the panel if we did an inverted roof assembly. So protected, like the insulation and ballast would have to be above the sheathing. Or rather the membrane. So what we showed, even with keeping the existing oil-fired boiler for the moment, we could achieve a 77 energy use intensity reduction of about 5,000 gigajoules per year, and a 69% greenhouse gas emissions reduction of 382,000 kilograms per year. So it, was not a complete success in terms of electrifying the building and eliminating fossil fuels entirely. We're still able to greatly reduce the emissions with this building at great capital cost. So the whole project would cost about $13.5 million. And as said before, that's not really viable to New Glasgow. This is like their entire capital budget. This is like, their annual capital budget's around that much. And it's for all of these projects, we kind of looked at, or wanted to present the breakdown of whether, where those costs went. So this was predominantly envelope related expense. Additionally, we estimate the cost replacement value of this building at 12 million. So I think we're going to encounter that a lot over the coming decades, that retrofits are needed. We really can't replace every building in our country from a resource perspective. When does it make sense? You've got to look at that cost replacement value of the building. And then to add solar panels to this building, the project would actually be 20 million. So we'd need another budget increase to get there. In terms of where the TCBO landed with this, spending the 13 million now would save about 11% over the next 60 years. So next up is Colchester's building. And so this was the water utility building again. This building is kind of a two-part building, which allowed us to study both a wood structure and a concrete masonry structure. The kind of part of the building with the gable roof is around a 2,000 square foot office space. That's the wood structure. And the other side is just under 6,000 square feet. That's a maintenance building. Building was originally a tree breeding center for the Nova Scotia Department of Lands and Forests, and it was built in just around 1979. And its current energy use intensity is 435 kilowatt hours per meter square per year, and that works out to 57,000 kilograms of CO2 annually. So our recommended design for this project was to add 2x6 recover wall panels on both sides of the building, and then to increase the roof insulation to effective R40. And we were not proposing to panelize the roof, rather we're actually suggesting that they would add new wood framed gable roofs over the existing roofs. Just that was the least expensive situation. And for buildings up to a certain size, I would say that's probably almost always going to be the least expensive scenario that we can come up with for the roof. Again, we had high performance windows. Again, we had a 90% efficient ERV, the TempF. And in this case, again, we couldn't make the business case for switching, for electrifying it yet. But we still found that they could get there was a solid business case for adding 42 kilowatts of solar. And so here's a sort of schematic. We have, the wall diagram is the same, but the roof looks more or less like a conventional roof. As I said, we just want to top up the existing insulation to, to greater depth. And so that's our sort of schematic or our rendering of what that building would look like. There would be solar panels on this face of the longer part of the roof. And in terms of greenhouse gas emissions, this work would represent a 79% reduction, so down to about 45 kilograms per meter square per year, or 45 kilograms of CO2e per year. And a 69% reduction in energy use, down to about 179 gigajoules per year. So again, even though we aren't decarbonizing the building fully yet, we're still seeing significant savings in energy and GHGs. This budget is much more palatable than New Glasgow, so around $2.3 million to do the work. Again, it's largely envelope related, and that's in both cases, compared to the other projects in this study, we, when we were able to get rid of the existing systems, we had sort of the mechanicals were kind of a substantial amount of that budget. So these two are not the pattern. In terms of the total cost of building ownership, over 60 years, we're saving them about $1.2 million. And so the difference between business as usual is about a 14% savings. So both of these buildings did not, the results were not as promising as our residential buildings, which had, at least a 30% savings. And that is what we found. That was the pattern across these municipal buildings, is that the savings were not as promising as in the previous residential projects. So finally, Halifax. This one's a little bit more of a good news story. So this is the Harrietsfield Williamswood Community Center. And this building is around 6,200 square feet. It was originally a fire station built in 1970 and underwent a major renovation in 1994 to convert it to use as a daycare and as a community center. This building, I think, try not to be judgmental about projects, but I'm like, do you guys see any windows? Like, it's just like kind of the most depressing looking daycare center I've ever seen from the outside. I think that they do okay, but I would love to give them some windows. This building has like concrete masonry units as most of the structure. There's a little bit of wood framed walls, but mostly CMUs, and then it has a timber roof. So the current energy use intensity of this building is around 146 kilowatt hours per meter square per year. And we thought that it would be useful to frame this like in comparison to other buildings in Canada of similar usage, because even though it's kind of like an uncomfortable building, like one of the main reasons why it was in this study was, you know, they'd like to get the energy use down, but occupants are very uncomfortable in both winter and summer in this building. But it has undergone, like it's got two kind of mini split heat pumps now, and it's had a lot of the superficial upgrades done. Like it's already been converted to LED lighting, for example. So compared to an average daycare in Canada, it's well, an average daycare in Canada is about 230 kilowatt hours per meter square per year, and an average rec facility that is used this way, like this one, you know, that's a gym that has community meetings, not one with an arena or a swimming pool, has a energy use intensity of about 308 kilowatt hours per meter square per year. So this building is performing statistically better than comparable buildings in Canada, but still needs some attention. And so this is about just under 31,000 kilograms of CO2e annually. So our recommended upgrade was to add 2x4 wall panels, or bringing it up to about or 25 rather, and to increase the roof insulation to our effective R35. And again, similarly to Colchester, we are proposing to do that through a new truss, just kind of a scissor truss that sits over top of the existing roof. Again, high performance pass windows and 90% efficient ERV. In this case, we are electrifying the building, so we're recommending a new electric boiler be installed. And the building can be brought to net zero performance with 69 kilowatts of PV. And here's a graphic that shows what it might look like afterwards. And you can kind of see the gray is the existing roof, and the white is a new roof that would be kind of sat over top of it on a little knee wall that runs the perimeter of the supporting walls. When we WUFI modeled this scenario, we there was a sort of bit of a risk involved associated with this kind of double attic scenario. And so we found that we actually need to make holes between holes in the old sheathing to make sure that those two attic spaces are continuous. So the risk kind of goes down considerably, or to almost nothing, as long as we can keep that, you know, as a continuously ventilated space. So the cost of this project is $1.4 million. Again, still a lot of envelope, but a bit more of the budget is going to mechanicals and electrical in this case. And the electrical is largely the solar PV here. And this was in the study, this was our best TCBO improvement. So if Halifax implements the recommended measures, there's going to be, or we estimate a 37% improvement in the TCBO. And interestingly, this was actually our minimum. So we were kind of like, this was the scenario we developed that was only aiming for 50% energy UI improvements with the addition of solar. But because Halifax's building had already kind of had a number of upgrades and it wasn't performing kind of, you know, as comparatively as badly as some of the other buildings, that's why we were able to achieve this with just a 50% EOI improvement. Definitely that is not the pattern that we have seen in other buildings. Not the rendering, sort of the outside of that. The other thing, we kind of like, there is an opportunity with buildings that, you know, if you remember back to the roof line from the first image, we had, you know, kind of a lot of different roofs that were intersecting. And so we proposed to just kind of make it one simple roof with the new trusses that are installed over top of that. And that simplifies the roof. It means you've got more surface area for solar panels, and it also will reduce their maintenance burden because I mean, that roof, the existing building, it's actually, there's a bit of a leak happening now where one of the roofs meets the other roof. Like it just eliminates some of the durability and servicing maintenance burden going forward. So our overall conclusions from this study were that we can achieve deep greenhouse gas savings on these buildings. Like every building, we were able to demonstrate some significant greenhouse gas reductions through, you know, through not just our recommended approach, but most of the approaches or scenarios we examined had promising GHG savings. Unexpected cost barriers. So none of the 6 buildings had a 20-year payback. NRCan really wants to see a 20-year payback to fund a demonstration project. We honestly didn't think we were going to be able to demonstrate a 20-year payback going into it when we're using the TCBO method. But again, we're trying to advance the conversation about the way that we evaluate the benefits of deep retrofits because they're so complex. Maintaining and rehabilitating existing buildings definitely reduces greenhouse gas emissions. So, you know, this was a sort of secondary priority in measuring this in this project because it wasn't part of the NRCan project requirements, but we did quantify this. And so if you go and read our report, you can find out what we found out about these. And de-risking panelized retrofits. So, you know, our primary goal was to explore panelized retrofits and see if we can remove some barriers to implementing them in Canada. And we felt strongly about the research in terms of the technical viability of panelized retrofits and scalability as well. It's, you know, the cost burden is just not there yet. And so right now we're really thinking hard about, okay, do we keep pushing this agenda and get some demo? I mean, we would love to get some demonstration projects off the ground and maybe on the verge of doing so. But the cost is not, you know, and because we're doing it, we're not doing it with like a pile of lightweight foam. The cost is higher than we would like it to be. And I'm done.
That was really great, Laurie. Thank you very much.
Yeah, I will say I put the email or the website address for Recover here because Recover, everything that we do is open source. Like we'll share everything within, you know, the owner's comfort limits in terms of these projects that we're looking at because it's so important that we understand how to scale retrofits. So all of the final reports for these projects are available at that website to download.
That's a great resource. It's a great resource, and certainly there hasn't been a tremendous amount of work in Canada, you know, on this. So, you know, you probably have the majority of the library at this point, or at least a big significant piece of it, I would imagine.
Yeah, there's a few others that are kind of acting, you know, working in the same vein. I think we're pretty much aware of everybody who's doing it. The other resource actually, there's so the organization that I sit on the board of, Retrofit Canada, they're assembling a case study library of sort of open source project data as well. And they actually have, they probably have more than us, although our reports are more in depth, they have more projects represented.
Okay.
So they're based in Alberta, but I think they aren't just Alberta projects. If you go to, I think it's retrofitcanada.ca.
Great. I do have a number of questions. There's a couple of questions that came from the audience, and I jotted down a number as well during the conversation, during your presentation. So maybe we'll jump into a few of those if you have a few minutes.
Absolutely, yes.
So the first one is very tactical, and I wanted to start with the tactical ones and kind of move out to more kind of holistic strategic questions towards the end. But the first question I wanted to ask you is just with respect to logistics of bolting on or connecting these panels to the existing buildings. Can you speak to the level of kind of intervention necessary with existing envelope systems to connect them? Is there extensive work to be done? I know you talked in terms of the roof, having limitations structurally so that, it would be advantageous to build new roof on top of. That seems less panelized to me. So like from the walls perspective, when you're shipping panels to site, how much work on the existing building is necessary typically?
So a bit depends on the building, the existing structure. So what we found is that, you're right. Across the board, what we found is it's really hard to panelize the roof. In most of the buildings, we either did a truss roof or we just did had to do a conventional retrofit, like with adding additional layers of XPS or something.
Right.
With the walls, so if you have an existing masonry wall, you do need to prove, so you need to do a bit of destructive testing and analysis to make sure that that structure is sound before you can tap into it. So a good example of this would be the Burlington Community Center that we looked at. And if the underlying structure is secure, basically it sort of depends. Like we can bolt the panels in there, or not necessarily bolt them in, but bolt the strapping to the building and then secure the panels that way. And then we do have for the most part, all of the walls that we looked at could absolutely take more weight. And so, that's also why adding a truss roof is not too challenging. But the part that we sort of wanted to be careful about is at the foundation. So our typical detail is that we put an L bracket, like a steel ledger at the base, which and then the panel is kind of bolted to that, and it is bolted into foundation, right, into poured concrete. And then depending on the height of the building, on some of the one-story buildings, all that was required was a strong connection there and a connection at the roof, and then the panel isn't really connecting in midway. And then in taller panels, we had to find another line of fastening at the midway point. So if it was a 2-story or 3 or higher building.
Sorry, in any of those examples, did you guys have to worry about seismic loading?
That's a good question. Nova Scotia's like seismic zone now, but like our seismic zone is not that, it's I think our wind is just as bad. So it's not even it definitely, our engineers didn't bring it up as like a limitation, I guess. I think it would be an issue if we were looking at BC. Actually, and Pembina Institute has done some BC projects. So research on this, if anybody's looking, that is a really good question. And then with wood buildings, basically we're tying in at the ledger boards, we're tying in at the roof, and again at the foundation. So, the panels aren't being tied back in, a million places. They're being tied in strategic structural places. So there has to be, that's one of the challenges with scaling is there's still quite a bit of analysis that has to happen to make sure that you're that the existing building can be tied into But it'll come. Like we've got to collect a lot more data before we can sort of establish the guidelines around it.
So I wonder if that reality, is a small barrier anyways to like true industrialization of this panelized retrofit strategy, right? Like I think the dream would be that you could create factories, distribute them across your geography, and just churn out panels, churn out something that's
Yeah,
pretty standardized. You can go to a catalog and you can piece it together like Lego bricks, and then throw
that's
your
the
cladding on
vision.
afterwards, right?
That is the vision. Like like really, if we think about our labor shortage, um, it's, I think, we can't standardize the buildings we're attaching them to, but if we can figure out enough buildings that follow enough rules to de-risk this approach, and then we have prefabrication facilities that are just, like what if builders could just call up a prefab company and it's like trusses now. The engineering can be a little bit in-house, um and it can just be applied.
Yeah, for sure. Um, there was a question, around payback period. Now, I appreciate the fact that your analysis was moving towards total cost of building ownership and a life cycle type of analysis, and I couldn't agree more with that approach. I think it's the right way to go, especially because buildings, like we're intending on these buildings to be, owned by somebody for long periods of time, right? We're not talking about short-term investments. But the industry still talks in payback. So I guess the question that was asked from the audience was around payback, and from all of the work that you've done, and perhaps what you've read from other initiatives, what do you gather is the kind of the quickest payback you might achieve with this strategy? And then a follow-up question to that would be, is there some sort of correlation to what the primary heating source, what the primary heating
um
energy is in that situation?
yeah. um I think the thing that we have found is that the payback, or the best kind of economic picture, is when we uh if the retrofit is going to be done to the building with a huge maintenance backlog. But what's funny is Halifax broke that rule. So like up until, like, all of the stuff we've looked at until that Halifax building, the buildings that were just in absolutely dire condition, the TCBO was way, way, way better. And that's because, I mean, I guess you're going to be doing that work anyway. So, at some point, it's either do that work or tear the building down. Um, and so, like, I'm still scratching my head about the Halifax one because it did break the rule. um, but in terms of existing heating, or in terms of heating system, and if that is a factor, like certainly, like the energy picture in Nova Scotia is very different than Ontario or Quebec or Saskatoon. And so I think it's like your fuel source and what you're doing there, and the likelihood of that place decarbonizing. Like, I mean, literally two of the buildings we looked at in Nova Scotia both still were using fuel oil, right? And so, like, and switching to our current grid, I think we're down below 50% coal in Nova Scotia now, but we're still, we've got a long ways to go before our electrical system is fully decarbonized either. But I don't think there was much consistency, I guess, in the results related to the
Okay.
heating system.
Okay.
Is that helpful?
Well, I think that is helpful. It's probably helpful for people who are watching this, and perhaps trying to project what you have done on their situation, because oftentimes there are underlying characteristics of your project site that are going to drive the result, right? And what you're suggesting is
Yeah.
perhaps how the building is heated and cooled at the moment is not necessarily one of those drivers, and I think that's a strong, it makes for a strong argument for doing this kind of broadly. So another question I had related to that is, did you find, because you did look at a number of kind of climate zones with your studies, Did you find that climate zone played a significant role in the analysis, or did it also
Mhm.
kind of wash out?
It kind of washed out, and I think maybe it washed out, I mean, but I think maybe I should also say that more research is needed because there's
Okay.
not that big of a difference between Ontario and Nova Scotia. And Saskatoon is quite a bit different. I didn't talk about the Saskatoon building, which I was pretty excited to look at that building. Again, it's a pre-engineered building. And so I'm kind of like, oh my gosh, if we can figure out how we're going, like if you think about the millions of square footage of pre-engineered buildings that are leaking energy in this country right now, like that is, that would be very meaningful
Mhm.
in our hitting our targets. But that building was a lead building to going in, even though they brought that building to the table because it still uses an outrageous amount of
Mhm.
energy. But it probably, if we were looking at a kind of more typical Saskatoon building, I might have more to say about it.
Yeah. Although I would argue that being a lead building doesn't necessarily mean that it's a high performing building, right? Because it
No, it
really
was,
depends on what you establish as your
yeah,
baseline,
yeah,
your checkbox system. But fair enough. Fair enough.
yeah.
Um, Another question. So, I'm going to move a little bit more now into like broader strategy and some of the cost considerations because, I see that as being a pretty substantial barrier to implementing this in a broad
Yeah.
sense. And certainly some of your total cost of ownership and kind of results kind of indicate that as well. For the costing that you did create, where do you see there to be potential movement in value with respect to the panel cost when you consider like economies of scale? Like if you if
Mhm.
you're looking at
Yeah.
making many, 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 many panels, like do you think there's room to reduce the cost of that system from what you estimate?
Yeah. Yeah. And that is, I'm quite sure that that's where a lot of the savings that Energy Sprung was able to achieve came in, was when they
Okay.
started really, streamlining their manufacturing processes. The situation we're in right now is really tricky. I would say it's funny because our this six this six building kind of project, the costing was worse than our previous two. But I'm also like, we were a lot more rigorous, I think, on the costing. We had it costed internally, and then we had a private cost consultant do it, also do it. And I think in this project, we really, like in the first two projects, we had manufacturers we were talking to who might be the builder to do it. And then in this one, we just assumed it was going to go to market. And so it would be more competitive. And so we were, I think, more conservative on that front. But the reality is we have so few options right now for who would be building them that it's going to have a premium at the beginning. It sort of only makes sense for us to do some demonstration projects, which will have a higher cost and and demonstrate proof of concept, and then hopefully we there's a few, I mean, I have kind of a network of passive house, guys who are making like prefab passive house panels that are similar to our panels for new builds. And there, some of those companies are interested in this. They just haven't kind of had this opportunity to do it yet. So that's where I see like maybe being able to uh, take something that's existing, like because the companies that are doing like prefab homes right now are not building to the performance level that we're needing these panels to be built to, like in terms of air tightness, etc. So I mean, in a lot of ways it's an entirely new industry. But
For sure.
and hopefully though, there's like, if you start to see, like when you start to see, look around with the lens of what buildings am I looking at that need a retrofit, like all you can see is like dollar signs if you were a builder who was like doing that. It's every building out there practically. So
Well, I mean,
um,
many have said that this decarbonization push that the globe needs to be on, right, to lower the impacts of climate change and to keep our warming to 2.5 degrees or less is probably one of the most concentrated opportunities from a capital perspective that we've seen in a good long time, because there's lots of room for building solutions, selling solutions, and implementing solutions. So it is a huge economic opportunity for many, I think. But in terms of dollars, so you talked about the total cost of ownership, and I know you're not using the words payback, and again, I appreciate that because I'm not a fan of the term payback. But did you have a look at in all of your analysis financially? Did you look at cash flows? Because you did speak a little bit about the results not necessarily being viable for some of the clients. So is that based on the total cost of ownership? Is it based on the percentage saved over 60 years, or is it based on cash flow?
It's based on cash flow. It's literally based on their current budgets and I mean, in the case of certainly New Glasgow, where it's like, oh, this retrofit costs more than a new building that would be purpose built, so it would obviously be exactly what they need. Whereas this retrofit, like them using that building, is like kind of a compromise already.
Right.
So it's more related to that. And certainly the TCBO is kind of like a cash flow. Like it's more like it's like, I'm not an economist. Please go call CFAR, who did our TCBO modeling, if you have detailed questions. But it's like a cash flow that has net present value captured as well. So it's the most comprehensive. Like, we're working with them because like we really want to be comprehensive about it. There's one other thing, or there's a lot of other things that aren't really captured in this, though, that we really need to, as a country, get a handle on, and that's like the social value. Like, because we need housing, we need like the healthcare dollars saved for making our buildings better is just not reflected anywhere, and is a huge like if we understood that better, we would spend more money on buildings.
I wonder too, like, I know that our current carbon tax system, which I think the country seems to be divided on. Well, a number of people seem to be divided on this. I think perhaps the scientists and those folks that are working the space are probably not divided on it, but that's focused on operational carbon. And I wonder if to make some of these initiatives more palatable, there is going to need to be kind of an embodied carbon equivalent, right? Which would, like the example that you just made, New Glasgow, it's less expensive for them just to raise the building and build a brand new one equivalent to their needs. Well, what happens if you start to put embodied carbon on top of that, and if there's a tax on embodied carbon, perhaps there's some savings there that can be found.
Yeah, that's something I've said for a few years, that we really need. Living in Halifax, where we've had like a spree of demolition of older buildings over the last few years. If you take a building to the dump, if that was carbon taxed, I really think that like there would be some equalization happening. And Halifax as a city has very like, they have a goal to retrofit every building by 2040, like publicly and privately owned, and influence that. And I'm like, all right, let's get the carbon tax on these demos then, because like that will really change the whole conversation.
Well, it would certainly level out. It would level the playing field, and it would allow you to have like a true and honest conversation about value, right? With respect to retaining existing or recycling it, whatever the case may be. I mean, you see it in more than just the Halifax or the Atlantic Canadian jurisdictions. I mean, Ottawa has similar targets, and I've often asked folks at the city how they intend on getting private landowners to move in the direction that they're expecting them to move. And it occurs to me that it comes down to access to capital. It comes down to dollars. And I see in all the things that you have said, like, is access to cash really the single most significant barrier for people?
Oh, I think affordability is the greatest barrier, but I also think that education is critical, because people don't appreciate like the full impact of their decisions. So, but I mean, it doesn't matter. Like, you can have all the goodwill in the world, if you don't have the money, it doesn't matter also. So, I mean, we are working on that. So like, going forward, Recover is like we're a baby organization, but we are gearing up to not just do studies, but to work as a retrofit accelerator where we'll be hopefully connecting owners to financing models or to funders and helping to actually get owners connected with somebody who will help them pay for the projects. And the whole reason for looking at TCDO is to essentially prove to people that they can't afford not to do these retrofits. Like certainly, I think we did prove that to Toronto Community Housing. That they're not doing our retrofit yet because they still have like a lot. They can kind of make up a lot of ground towards their 25%, focusing first on their towers, but they will be moving to their townhouses.
Right.
Yeah.
Of course, the tower retrofit program has been around for more than a decade, almost two, I think. I remember looking at it many, many years ago when I was just starting out as a consultant out of school. So to say that they have to work on that first is disappointing that they haven't maybe made that much progress. But
I mean, I think that they, that they haven't been focusing on it. I do think I think that they have decarbonized something like 9% of their portfolio through tower retro or larger building retrofits so far. So they've got a ways to go before they get to 25, but hopefully they do it.
So I have one more question. Maybe this is the most philosophical of the bunch, but if you look across the country, there's probably over 15 million existing homes that will need some level of work done to them in order for us to achieve our 2050 aspirational targets goals in terms of carbon emissions. Are we barking up a tree that we're never going to get up? Is this something that is achievable, do you think, based on what you've studied, what you've seen, and what others around you are?
I mean,
it's a bit of a downer question to end with, but I'm hoping what it does is it spurs people to consider, individual choices.
I mean, I don't know if it's achievable, but I think we have to get close. Like we really do need to, like, not just for energy but reasons, but because of resilience. I mean, fire and violent storms are like two reasons why people need to invest in their homes just for their security. And I think that one of the things that I think gives me hope is that like it's not like we actually have the technical solutions. It's a money issue. And like if we can get the government to influence the financial system to mobilize, that's when we're going to really start to see transformation. So there's I kind of like I jumped into this feet first because I like solving technical problems. And then I'm telling you, it's not even a technical problem, is my current feeling. We have a lot of smart people in our industry who can figure out the how to hang things off of buildings and how to deal with moisture risk and things like that. It's money. So that's and there's a conference, Retrofit Canada, which it's like about this year will be the fourth year. The first year it was kind of like policy people, and the second year was kind of policy and technical and a little bit of money, and last year was all money people. So I feel like they know that there's money to be made there, so they've just got to figure out how they're evolving as a body. And I think we might start to see a shift.
Absolutely. Well, listen, thank you, Laurie, for making the time to share, all that you've learned, while studying this and working on these projects with us, and for engaging in this conversation and following. I've really enjoyed it. I think there's lots of great meat here for us to carry forward, and I would really hope that folks that are watching this or have watched this will find some inspiration in the work that you've done and what you've said. So thanks again for taking the time, and enjoy the rest of your day.
Yeah, thank you. Happy weekend.
Absolutely. All right. Thanks, everyone.